All right, let's dive right into one of the biggest, most baffling mysteries in all of modern physics. Think about this. We have this incredible theory. They call it the theory of almost everything for a reason, and yet it has this massive, gaping hole. It completely, utterly ignores the one force you and I feel every single second of our lives: gravity. So how on earth is that even possible? Well, we're about to put on our detective hats and investigate a true scientific whodunit.
So, yeah, that's the big question, isn't it? How can our greatest intellectual achievement, this masterpiece of understanding the universe, have a giant, gravity-shaped hole punched right through the middle of it? I mean, it's a puzzle that has kept the smartest minds on the planet scratching their heads for decades.
All right, Section 1, the missing piece. So, where does any good investigation begin? You got to look at the star witness, right? And in our case, that's a theory so powerful, so precise, it's known as the Standard Model of particle physics. And look, the Standard Model, it's just nothing short of a triumph. It's our best recipe for the universe. It perfectly describes 3 of the 4 fundamental forces: electromagnetism, the strong force, the weak force. It explains all the tiny building blocks of reality, quarks, electrons, the whole gang. And the crazy part? Its predictions have been tested and verified with just mind-boggling accuracy. This thing is the absolute bedrock of modern physics.
And yet, for all its glory, it has this one massive blind spot. I mean, the force that's literally holding you in your chair right now, the force that keeps our planet from flying off into space, the one that shapes entire galaxies, it's just not there. It's completely gone from the equations. So you have to ask, why? What's the deal?
Okay, Section 2, the case against gravity. To figure out why gravity got kicked out of the club, we need to look at the evidence. And it really boils down to 2 key clues. 2 reasons why physicists basically have to just ignore it when they're working on the quantum scale.
So clue number 1 is just how incredibly weak gravity is. I mean, on the scale of tiny little particles, it is absurdly, almost comically weak. Just look at this number. That's how much stronger electromagnetism is than gravity between a proton and an electron. Gravity is so feeble down in the quantum world that for most experiments, it's basically a rounding error. You can just pretend it's not there, and your math still comes out pretty much perfect.
But that's the small problem. There's a much deeper, much more fundamental issue. When physicists try to do the obvious thing, treat gravity just like the other forces, and describe it using the rules of quantum mechanics, the whole thing just breaks. The math completely falls apart.
Now, this problem has a very technical, kind of scary name. It's called non-renormalizable. But don't worry, it's just a fancy way of saying the theory is totally busted. When you try to do the calculations for a quantum gravity interaction, the equations just spit out gibberish. Specifically, they spit out infinities. These answers make no physical sense at all, and all the clever mathematical tricks physicists use to fix these kinds of problems for the other forces, they just flat out don't work on gravity. It's a dead end. A complete brick wall.
Okay, Section 3, rethinking space and time. So if the old framework is a dead end, what do? Well, maybe you need a whole new framework. And this leads us to a radical new suspect in our investigation. A theory that says, hey, maybe the problem isn't gravity. Maybe the problem is how we think about space and time itself.
Enter loop quantum gravity, or LQG for short. And its core idea is, well, it's absolutely revolutionary. Instead of trying to shove the square peg of gravity into the round hole of quantum mechanics, LQG just flips the whole table. It says, what if space-time itself is quantum? What if it's not some smooth, continuous backdrop, but is actually made of tiny, fundamental, indivisible chunks?
This comparison here, it nails the difference. We all know the old idea from Einstein, right? Space-time is like a smooth, stretchy rubber sheet. But LQG says, nope. If you could zoom in way in, you'd see it's more like a t-shirt, a fabric woven from individual, distinct threads. So in this picture, space-time isn't just the stage where the play happens, it's one of the actors in the play.
So Section 4, a universe of loops. I know, this probably sounds like something straight out of science fiction. But this idea is grounded in decades of really serious, really difficult work. So let's actually look at the evidence for this totally new way of seeing the universe.
Yeah, this theory didn't just pop into existence. The story really starts back in 1986, when a physicist named Abe Ashtekar found a new way to write down Einstein's equations. This was huge. It created a whole new mathematical language that people like Ted Jacobson, Lee Smolin, and Carlo Rovelli then used to build a quantum theory based on these loops. And then, bam, the huge breakthrough in '94. Rovelli and Smolin showed that if this theory is right, then area and volume themselves are quantized. They come in tiny little packets. It means there's a smallest possible size for anything in the universe.
And this quote right here just drives that t-shirt idea right home. The smooth, continuous reality we see all around us, it's basically an illusion. It's just a large-scale effect of this incredibly fine, underlying quantum fabric, a fabric woven from what physicists call spin networks.
Okay, so once you start thinking of space-time this way, you get some really mind-bending consequences. Let's talk about the Big Bang. In the old story, the universe started from a singularity, an infinitely dense point. But in LQG, no singularity. Instead, we get a big bounce. The idea is that a previous universe collapsed in on itself, and just when it was about to become a singularity, the quantum nature of space itself pushed back, and it bounced, expanding out to become the universe we live in today.
It doesn't stop there. The theory completely reimagines black holes too. Forget this singularity at the center. LQG predicts something called a Planck star, an object that's unbelievably dense for sure, but it has a finite size. It's held up from collapsing forever by the very fabric of spacetime. And what's so cool about this is that it not only gets rid of those nasty infinities, but it might just solve some of the biggest paradoxes about black holes that have been bugging physicists for years.
All right, Section 5, the quest continues. So, is that it? Is loop quantum gravity the smoking gun? Case closed on the missing force? Well, not so fast. The investigation is still wide open.
For all its elegance, LQG has some serious hurdles to clear. For starters, it has a really tough time fitting the other particles, the ones from the standard model, into its picture. It tends to create these unwanted mirror particles, which is a big problem. And it also hasn't fully cracked how to show that the smooth world we see, Einstein's world, naturally grows out of all these tiny quantum loops. That's a huge step it still needs to take.
And of course, you can't talk about quantum gravity without mentioning the other main suspect, string theory. This table really lays out how different these two theories are. I mean, look at this. LQG works in the 4 dimensions we know and love. String theory needs 10 or even 11. LQG's whole game is quantizing spacetime, while string theory is all about unifying everything by saying it's all made of tiny vibrating strings. They are two completely different philosophies, two rival gangs fighting for the same turf.
And that really brings us to the biggest question of all. This whole case of the missing force. It's not just about finding a neat little box to put gravity in. It's about discovering the true, fundamental nature of reality itself. So will the final answer be made of loops? Or strings? Or something we haven't even dreamed of yet? Whatever it is, the search for that answer is, without a doubt, one of the greatest intellectual adventures humanity has ever been on.